Introducing Precision Now, an innovative approach to data analysis, including dDesk, dDock, and dDockDT. Let's begin by looking at dDock and why it's your new favorite data solution. Your plant is generating an enormous amount of valuable data and information that could be used for any number of purposes, including automated control, maintenance scheduling, operational efficiency, risk assessments, and so much more. However, the sheer volume of data has made the extraction of that information difficult previously. dDock changes all that. dDock is a real-time data analysis platform that is connected online to your data source and is able to receive and send data. It is able to run native and non-native real-time data analysis modules that are user-configurable. It is also capable of assessing your data quality, notifying operators of problems, and when appropriate, can be used to substitute alternative data, and ultimately will help you realize the benefits of your data collection efforts. Most importantly, what is the opportunity that dDock is providing? dDock enables users to manually import historical data, to analyze trends, understand the causes of process upsets, and enhance process understanding and knowledge. For real-time applications, dDock responds the moment new data appears. It automatically runs the appropriate routines and delivers a result. That output is fully user-definable. It could be an alarm, an updated trend graph, a calculated quantity, or any other outcome you've designed. By giving your team the power to customize how data is analyzed and presented, dDock puts real-time decision-making in your hands. How does dDock help you realize these benefits? dDock is a real-time analytics software package that can be linked directly to your plant's OPC or ERIS server. Simply drag an OPC client object onto the drawing board. Choose the appropriate settings for the data access method. Enter the node associated with the data to be accessed, and that's it. The data will now seamlessly be transferred to dDock for further analysis. Anytime raw data is analyzed or manipulated, it is important to verify that those actions are appropriate. That is, there needs to be continuous verification of the raw and alternate values. Traditionally, this verification might take the form of control charts or comparisons to reference values to signal problems. More advanced approaches involving principal components or similar analyses can also be used to indicate if the raw data is deviating from its normal operating range or if the alternate value is appropriate. There is no getting around it. Your data will have errors in it. Those errors may be obvious, or they may be more subtle. For example, the data simply might not exist. Maybe the lab sample wasn't taken that day, the sensor was off, or communication was interrupted. Other errors will also occur like zero values, constant slopes, or constant values. Calibration errors will also occur, like drifting values or offsets. In order to realize the potential benefits from your data, these errors need to be detected, and automated detection of those errors is now possible. Detecting errors is essential, but effective correction is what drives process improvement. dDock offers a way to automate error detection and correct those errors in real time when necessary. This means that in addition to storing the raw data, you can also store cleaned data and metadata about its quality. This ensures that the highest quality information is always available, allowing real-time applications to operate with the best possible data. Not only do these real-time applications benefit, but performing data analysis during the storage process saves time, effort, and money when the data is used in the future. dDock uses these steps to transform your data into actionable information which can be used for optimizing plant performance, minimizing energy consumption, and more. So, what do you need to run dDock? The software required to run dDock for analyzing historical data is simply an active dDock license. For analyzing real-time data, you will also need an active server API for data acquisition. Now let's transition from talking about dDock to looking at the digital twin capabilities included in dDockDT. What is dDockDT? It is a digital twin platform that has all the features of dDock, plus the ability to run and manage the data to and from a simulation. The dDockDT interface is used to set up the connections between the operating real treatment plant and the simulation. Data from the treatment plant goes through the data quality steps, transforming the data into simulation-ready inputs. The simulation results are then sent back to dDock, where they are transformed into actionable information to support decision-making. Let's start setting up your digital twin in dDockDT. The first step in setting up a digital twin is to import a process model. In this case, we will import a Sumo process model. Click on the Import Sumo Model menu item to open the Import wizard. Step 1 of the wizard involves opening Sumo and running the model. Then, following the wizard instructions, you will save the Sumo starting conditions through the core window, which is accessed through the Sumo interface. The next step is to copy the project directory into the dDock wizard. This is done through the Sumo GUI by accessing the View/Directories menu and choosing the Project Directory menu item. The last step is to give the Sumo model a unique dDockDT channel name. In this case, we called it Imported Sumo Model for simplicity. Your Sumo model has now been imported and is available to be dragged onto the drawing board. Because the model has been imported, the Sumo interface is no longer required and can be closed. Note, however, that even with an imported model that doesn't require the Sumo graphical user interface, a valid license for the model, Sumo in this case, is still required to run the digital twin. The next step in the digital twin setup is to drag a simulation control module onto the drawing board and set up the simulation parameters. In this case, we will set up the model with one input, the influent flow, and two outputs, effluent ammonia and nitrate, to make the example as simple as possible. There is no limit to the number of inputs and outputs, and these could have been 100 just as easily. As the Sumo model has already been imported, we will uncheck the Import Sumo option, and we will specify which version of Sumo the model was created in. Next, we will set the model alignment and communication times, the simulation type, steady state or dynamic, and the model input and export variable names. Note that in the initial step 1, one input was specified and one input box is provided. Similarly, two outputs were specified, and now this step has two entry fields for model output variables that will be returned to dDock from Sumo. The digital twin requires a data source from the operating plant. In this case, we will access the real-time data through an OPC client communicating with the plant OPC server. Here we enter the client name, OPC address on the network, and the node that contains the data we want. Next, we specify all the options for the data acquisition. Do we want to access historical data, as well as the real-time data? How often do we want to query the server for new data? And what time zone are the server and local machine working in? In this case, we are setting the query up as two separate data queries. In the first case, we will pull the model input data, which in this case is the measured influent flow. And in the second case, we will query the measured values that we will compare the model output to. So, in this case, we will feed the model the measured influent flow, and we will compare the model predicted effluent ammonia and nitrate to the plant's measured values. We will pull the measured data from the plant using two different OPC client objects for visual simplicity. But it could have been done with one OPC client. The architecture of dDockDT doesn't care how many objects you set up. The fourth step in this process is to connect this real-time data to a data flow scheme. Because the OPC client in dDock is accessing data locations in a data stream from the OPC server, it is good practice when multiple variables are being accessed to assign the incoming data to a channel with appropriately labeled attributes. In this case, the second OPC client is accessing the effluent ammonia and effluent nitrate, so we will create a channel with those names in the appropriate entry fields. This newly created channel is now available in the Output Channels menu and can be dragged onto the drawing board and connected to the OPC client. The first OPC client is accessing only the influent flow data, so although it could be attached to a labeled channel if desirable, it is not necessary and it can be directly connected to the Sumo simulation controller as shown here. We are now ready to connect the Sumo model that was previously imported to the simulation controller. We do this by locating the Sumo model in the Output Channels menu and dragging it onto the drawing board. Then we connect the model to the simulation controller top pipe connection. Recall that in this simple example, Sumo will be returning the model predicted effluent ammonia and effluent nitrate. So we will right-click on the simulation controller output pipe and create a channel with effluent ammonia and nitrate attributes. Note that the order of the attributes corresponds to the order of the variables defined in the simulation controller setup. Once the channel is created, the channel is available in the Output Channels menu, can be dragged onto the drawing board, and connected to the simulation controller output pipe. This very simple digital twin is now complete. The influent flow from the plant will be accessed in real time and sent to the Sumo simulation controller that is connected to the imported Sumo model. The model is continuously running in the background and responding to any new data immediately. The output from the simulation, in this case the effluent ammonia and effluent nitrate, have been assigned to an output channel and is readily available for further analysis. For comparative purposes, the plant-measured effluent ammonia and effluent nitrate are also being accessed in real time and assigned to a separate channel. In the simplest case, one might simply plot these quantities on a couple of time series plots and compare the model-predicted and plant-measured values. In a real digital twin, we would expect more model inputs and more model outputs. But the purpose of this demo is to show how easy it is to set up a digital twin using dDockDT. There is no need for any external applications as dDockDT controls all of the data flow from the plant, as well as to and from the simulation engine. One feature of dDockDT is its ability to ensure data quality and substitute alternative values when an error is detected. In the previous digital twin, the influent flow as measured from the plant was fed directly to the model without any error checking or data analysis. Here we show a more complicated digital twin setup, where we are illustrating the need for real-time data quality assessment prior to sending the data to the process model. In the one case, the model is simulated with the raw flow data received directly from the plant. In the second case, that same data is first subjected to a series of data quality and outlier detection algorithms. In this case, there is an underlying flow data soft sensor model running in parallel, such that if the detection algorithms indicate a problematic data point, dDockDT immediately substitutes the soft sensor value. The resulting output from these data analysis steps is a corrected data series that is sent to the model, thus minimizing the potential for simulation errors. The added advantage of this pre-processing is the ability to signal that a faulty sensor has been detected and potentially improving the uptime of the plant sensors. Here, we show the impact of correcting faulty data on the simulation output and how the detection of problematic data before it is sent to the model is critical for an effective digital twin. The same is true for the simulation output and any data that the model output might be compared to. That is, all of the data received from the plant should be subjected to a rigorous assessment of its data quality to ensure that the model output is accurate and truly reflects the behavior of the process at all times. Using dDockDT, this process is automated, occurs in real time, is continuous, and the algorithms included with dDockDT can be customized to achieve the most appropriate result for any given facility or application. The analysis and data flow options are endless and only limited by your imagination. Now that you've seen how easy it is to set up a digital twin using dDockDT, why not see it in action for your own operation? Head over to www.primodal.com, click Contact Us, and fill out the Get in Touch form to schedule your demo, and start improving your plant operations today.